Hi, Michael Wolf, PGI compiler engineer. Today we'll be talking about managed memory and how to use managed memory with the PGI OpenACC compilers and what effect that has on your execution. So what is managed memory? Managed memory is dynamically allocated memory that's allocated in such a way that the NVIDIA CUDA device driver will automatically detect a page fault and move data from the CPU system memory to the device memory and back on demand. Let's see how this works. Here I've got my CPU with many cores and my CPU system memory, very large system memory, connected through a direct link there. I've got my highly parallel GPU with many processing elements, or SMs, however you want to call that, and a very high bandwidth but significantly smaller device memory. And a connection between the two. Today this is mostly PCI Express. On the new IBM Power 8 Plus and Power 9 systems, this might be an NVLink. So with managed memory, I allocate the memory using a different call. It's not just a plain malloc call, it's a CUDA driver call. It allocates a big block of memory. It's paged, as memory normally is. But when I launch a device kernel over here, and it accesses some of that data, the device will actually take a page fault. And then the NVIDIA CUDA device driver will say, oh, he needs this page from this block of data. And we'll do the appropriate transfer to get this data over here. And some other PE over here might take a page fault and need some other block of data. So that block of data will get paged over here. And the data gets paged over on demand. When locality works, and locality usually works, all the data will stay over here as long as it's only being referred to on the GPU. If the host then refers to the same data, then the host will take a page fault, and this data will get paged back over into the system memory. Now, you can run into problems if you can get thrashing between the two. If they're both accessing the same data frequently, then automatic data transfer maybe isn't the best option. It's the same, you can get cache data transfers, cache thrashing between multiple cores on a CPU if they're accessing shared data and writing to the shared data. So I'm going to be doing my experiments on two identical systems. These are two Haswell systems, dual sockets, 32 cores on each system, each connected to 2 Pascal GPUs, although we'll only be using 1 GPU for these experiments. I will build and run the SpecExcel OpenACC swim benchmark. The swim benchmark has an outer timing loop, and in each time step, it does a data update between the host and device. When using managed memory, that data update is essentially ignored because there's only one copy of the data. It's the data that gets moved. It doesn't get copied back and forth. When the host then refers to the data, it will get paged back to the host. Later on, when it's referred to on the GPU, it will get paged back to the GPU. In the upper window, I'm going to build this with normal options. Because I'm building for a Pascal, I'm using T equals Tesla :CC60. In the lower window, I'm going to build the same program and add the managed option. The managed option only affects dynamically allocated memory. These are the allocate and deallocate statements in Fortran, new and delete in C++, malloc, calloc, and free in your C program. Static data, global data, local data to a function, those will always be in system paged memory. They're not going to be used using the managed memory option. Now I'm going to run the reference data set on each of those benchmarks. If you're a CUDA Fortran programmer, there is a managed option for allocatable data that will give you the same benefit as the managed attribute on the TA option. In fact, if you mix your CUDA Fortran data with OpenACC kernels, then you get the same benefit with managed memory that you would have had if you had used the Tesla :managed option for that array. So you see the programs here are still running. It's going to take about 30 or 45 seconds. When you might want to be using managed memory, when you're initially porting a program from the CPU to CPU plus GPU, and most of your data is dynamically allocated, the initial port can be more straightforward by starting with the T=Tesla::managed option. With Tesla::managed, the data directives and the data clauses are essentially ignored for the data that lives in managed memory, because the NVIDIA CUDA device driver will be moving the data back and forth from the host to the device, and from the device back to the host. The second option is if your program uses a lot of Fortran-derived types or C++ classes that contain dynamically allocated members, using managed memory avoids the problem of having to transfer all the sub-arrays or the sub-elements for each member of the derived type or the class. In particular, the pointers are actually the same on the device and the host for managed memory, so pointers still work on both sides. Keep in mind that data transfers will generally not be asynchronous between the host and device. They're transferred on demand, which is one way of saying just too late. So here our executions have finished, and what we see is in the uppercase, the normal case, it took 49 seconds. The lowercase with managed memory took just over a minute, so that's about a 20% performance decrement. Another interesting point here, if you look at the difference between the user's time. In the uppercase, the normal case, was 41 seconds of user time. The lowercase was only 30 seconds of user time. What's going on here? In the uppercase, 7 seconds of system time. In the lowercase, 30 seconds of system time. What's going on there? Well, you can think of the user time as the time spent running your program and in the OpenACC runtime on behalf of your program. In the uppercase, this takes a little bit longer because all those data transfers, the data transfer happens from the device to host pinned memory, and then the host has to copy that data back into the user space. So there's this little extra loop in the OpenACC runtime to do that transfer from the pinned memory into the user space. That doesn't exist down here. On the other hand, with the uppercase, it only takes 7 seconds of system time. That's the time that the CPU is waiting on the GPU. There's something going on in the GPU. Either it's waiting for a data transfer or it's waiting for a compute kernel. In the lowercase, it's 30 seconds because, well, while the GPU is executing, now it has to page the data over, and the CPU has to wait while the data is being paged. And when the CPU needs some data from the GPU, it has to wait for the data to be paged back. And that's the overhead of using managed memory. Now, in this particular case, most of the data is going to live on the device. But because there's an update every iteration of that timing loop, there's paying a significant cost here. In some cases, the cost is almost unmeasurable. In some cases, it's actually quite significant. We'll see that in the next video when we talk about the improvements that we've made in the PGI 17.7 implementation of managed memory. Come back for additional information, tips and tricks on how to use the PGI compilers with OpenACC and GPU computing.